and it allows superconductivity to survive into the large magnetic field regime and enter the Majorana regime.
Shovik, what happened? Did we lose the speaker?
I think so.
Yeah.
I got a question.
What happened?
To
Did we lose
answer.
the speaker?
Yeah. I don't know. I mean,
I think so.
yeah. Okay.
I got a question.
What happened?
To
Did we lose
answer.
the speaker?
Yeah.
It's back. Yeah.
I think so.
And something popped on my screen, and I pressed
I
it.
got a question.
What happened? Did we lose the speaker?
Yeah.
It's back. Yeah.
I think so.
And something popped on my screen, and I pressed
I
it.
got a question.
What happened? Did we lose the speaker?
Yeah.
It's back.
Okay, are we back?
Yes, Sergey, please go ahead.
Okay, I apologize. I wanted to remove a window that popped up, and I think I pressed leave the meeting.
Yes, Sergey, please go ahead. Yes,
Okay,
Sergey, please
I
go ahead.
apologize. I wanted to remove a window that popped up, and I also hear myself like 5 times.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Whoever is recording, can you just mute your
I also
computer?
hear myself like 5 times.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Whoever is recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Whoever is recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Whoever is recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Let the host be recording, please mute your own computer.
Yes, Sergey, please go ahead. Yes, Sergey, please
I
go ahead.
apologize. I wanted to remove
Okay, I think I managed to fix it. Something bizarre happened. One of the techs logged in to initiate the YouTube stream. Somehow that caused the whole thing to go on a loop. Okay, I think it should be good now. Request everybody else to mute except the speaker. And sorry about this Majorana loop.
Yeah, that was fun.
This is a new one in 1.5 years of Zoom.
Yeah. We discovered the new effect. I think we should all write a paper together about it.
Go ahead, please.
Okay. Yeah. Well, I don't want to discourage people from asking questions, But yes, there is this danger that we will go into another time loop here.
But maybe this is a good place to pause and see if anybody has questions. Please raise your hand.
I thought Mandar had a question. Is that?
Mandar?
No, I didn't have a question. Sorry. It's okay. There was chaos. So it's okay. Let's continue.
Okay. Yeah, please, if you have questions, just use the raise hand and then we will pause and questions on. Yeah. Okay.
Okay, yeah, let's do the raise hand. All right, well, that was I guess, the theory introduction. I talked about how spin orbit makes peace between superconductivity and magnetic field and how it's an important ingredient for us. And yeah, indium antimonide has the largest spin orbit interaction of all their family of materials, which are known as 3-5 semiconductors, like gallium arsenide is the most famous representative of that family. Now, this is now beginning into the experimental introduction part. So I told you it's verifiable. What I meant is we have this method of doing a tunneling measurement in these devices, and we find these zero bias peaks. So this is how it works. You have a nanowire, and yeah, it's coupled to a superconductor on top, and presumed locations of Majoranas are marked by stars, and they are on the edges of this so-called topological superconducting state, or this Kitaev spinless p-wave regime. Now, underneath the wire, we have electrodes that don't make contact to the wire. We call them gates. So they can change the density of electrons in the wire or a chemical potential. And especially here on the edge, the green gate, we can make it very negative, repel all the electrons from this region and create a tunnel barrier. So then the left side of the device acts as a tunnel probe on the right side of the device. So we apply voltage to this non-superconducting contact. Electrons have to hop over the barrier, tunnel through the barrier, and then they're drained through the superconductor where we measure current. So that's a circuit, and so it's a tunneling transport measurement, current voltage measurement, but we always plot conductance. So here on the left, it traces our conductance. So this is our old data, and these both are from the same materials. It's niobium titanium nitride on indium antimonide nanowire. So the older experiments, we are now exploring different superconductors like tin or things like that. But all these data have these features, like, for instance, look at the bottom trace on the left. It has the two peaks at finite voltage bias on the battery, so about 250 microvolts plus and minus. Those are the manifestations of the induced gap from the superconductor in the semiconductor. So as an induced superconducting gap, you can see that inside the gap, conductance is suppressed. Oh, it's not zero, but it is suppressed. And then all the traces are offset for clarity, and they're for different magnetic fields, about 10 millitesla steps. So at around 100 millitesla, so when we add magnetic field into the mix, we start seeing the zero bias peak feature. And one of the most interesting things about it that we noticed right away was that once it appears, it doesn't move away from this point that it appears in zero bias. And that is unusual because, like I said, in indium antimonide, G factor is 50. So some kind of state that has spin, an electronic state, should move very rapidly through the screen. For instance, in 1 Tesla, it might acquire Zeeman energy of 1.5 milli-electron volts. So on the right side here in color, if we start at 1 Tesla, we go to 2 Tesla, we expect a resonance that starts on the bottom and crosses all the way across, if it's due to a quantized electronic state with a G factor 50. So the zero bias peak here in the middle of the screen is dramatically robust. So over a 1 Tesla, we can see it kind of pinned to zero. And so that's what we explore as a signature of Majorana fermions. Now, this color scale representation is the one I'm going to use more often, and has the same features in it, like bright red bumps here at low field, those are the edges of the induced superconducting gap. And inside the gap, black is a suppressed conductance. So it's not zero, but it is suppressed. And then this streak, like I mentioned, is a zero bias peak that appears at finite field. And then there's all these other states that, we can explore, but we still don't know precisely what they are. I see a hand, Arindam.
Yeah, can I quickly ask a question regarding the choice of indium antimonide? Is it primarily because the G factor is very large, or there's any other reason, so choosing over indium arsenide or any other nanowire with strong spin orbit coupling?
Yeah, so there are several reasons, in fact. Yes, I only spoke about G factor, and I also mentioned spin orbit interaction being strong. So it's indium and antimony are heavier elements, so the band gap is smaller. It means large spin orbit and large G factor. But another consequence of small band gap is the electrons are light, effective mass is low, and mobility is high. So in a reasonable size wire, like 100 nanometers, which we can handle with nanofabrication very nicely, electrons occupy the whole cross section. So the de Broglie wavelength, let's say, of these electrons is larger. So they are more quantum, sort of, at reasonable size systems. So we don't have to fabricate one atom thick wires. It can be 100 atoms across. So that's an advantage. Long mean free path is good because that's one of the unspoken critical properties for all Majorana systems, because you're trying to create P-wave superconductivity, and disorder of any kind, magnetic or not, suppresses P-wave superconductivity. There is no theorem that protects superconductivity from disorder for P-wave. And finally, the last property that's good is easy contact to metals. So when we put down a superconductor, this creates a possibility to transfer electrons between superconductor and semiconductor without a Schottky barrier or something like this. So you can actually induce strong superconductivity in a semiconductor. Even some theorists say it's too strong. We have to dial it back a little bit. Right? But if we had a Schottky barrier, it would just be a non-starter. So then between, let's say, indium antimonide and indium arsenide, those are pretty similar. But indium arsenide tends to have a lower mean free path, a lower G factor, a little bit lower spin orbit, a little bit higher effective electron mass. And it also, those nanowires often have crystalline defects in them, where the crystal structure rotates like this along the wire, and that probably contributes to shorter mean free path as well. So indium arsenide and antimonide are pretty similar, but antimonide still wins.
Right. Oh, thanks, Sergey.
Yeah, sure. Okay, so we've been exploring the zero bias peaks for a while now, right? Since 2012, or actually 11, when we started seeing them, 10 years, let's say. And we learned that they satisfy many Majorana signatures, but despite of that, there is another effect that can present itself very similar and requires extra care to tell between that and Majorana. So this is basically the summary of the last 10 years in a cartoon form. So we wanted to be Majorana, and we wanted to look like the top picture, two well-separated wave functions on the left and on the right. Remember, we're splitting an electron in two Majorana wave functions. And now I plot them with some kind of spatial profile. So there's some kind of oscillating and decaying wave functions along the wire. And when they're well separated, then the overlap between the green and the red is small. So that's the topologically protected Majorana zero modes that are very amenable to braiding and topological quantum computing, and have very clear signatures, and that's what we want. Now, if we add things like disorder or finite wire size, then the green and the red wave functions may actually overlap significantly. So that's the middle picture. Well, it maybe still originates from the same physics, from the same 4 ingredients with spin orbit and superconductivity, but the system size is too short, and it is like a partially separated electron, or sometimes people say quasi-Majorana. So that's still interesting, but more difficult to unambiguously say that it's Majorana. But what's more, even when we consider completely non-Majorana states, we call it trivial Andreev bound states. So these are states confined inside the nanowire. They're discrete states, partially confined by the superconducting gap, and so partially confined by Andreev reflections. That's why we call them Andreev bound states. Those states can also give zero bias peaks, and under certain conditions, with some fine tuning perhaps, look very similar to Majorana signatures. So here's an example so from our lab, but a diagram is from this paper that first studied Andreev bound states and quantum dots as a function of magnetic field, right? Magnetic field is important for Majorana. So the physics of it is basically Anderson impurity model. So you have a lead, which is in this case superconducting, and it's coupled by some rate to a dot, which can have a spin on it. And you study the screening of the spin by the lead, and the parameters are on-site energy and coupling rate, and you can see all that represented in this diagram. So let's say when the tunneling rate is 0 here on the bottom, then we put one particle on the dot and it has spin up or spin down. Those are the ground states. We add another particle, it makes a spin singlet. So that goes, that would be the excited state. But then if we couple it stronger and stronger to the superconductor, that spin on the dot gets screened. And it's also similar to Kondo physics, when a spin on the dot gets screened by a cloud of electrons. But because now we have a superconducting lead, it's screened by the superconducting condensate, by the BCS. So it makes a BCS singlet. Ground state becomes a singlet when the dot is coupled stronger. And there is a quantum phase transition at the boundary. And when we hit that transition, the energy difference between the ground and excited state goes to 0. And when we do transport measurements, when we tunnel into the nanowires, what we see is transitions between ground and excited states when we add one particle. So when the ground and excited states have the same energy, we will see that transition at 0 energy or at 0 voltage in the measurement. This is how it looks. So here, for instance, at 0 magnetic field, we have these bright states. That's the ground to excited state transition, or a resonance in tunneling at finite voltage. So nothing at 0 voltage, nothing sharp anyways. And then when we apply magnetic field, quarter Tesla in this case, that's when we hit the transition, the quantum phase transition, as a function of magnetic field in this case. And we have a 0 bias peak. It is relatively short, but it is there. And then when we keep going, we start seeing these kind of loop shapes, and the 0 bias peaks move around. So as a function of gate voltage, we see all these different pictures. For instance, look at 0.78. We see resonance at positive voltage, resonance at negative voltage meet and make a 0 bias peak for a very short range in magnetic field, and then they split further. So this is just, think of it as Zeeman splitting of spins. There is Andreev bound states at finite bias, and then they Zeeman split and cross at 0 bias, and they just keep going. That's the kind of a generic situation. You know, all the many body physics of this process is buried under the rug. You can just think of spin splitting. But then adjust the gate voltage a tiny bit, 0.76. You see they split again from finite bias. They hit this point and they just never split again. They just stay at zero bias for a while, for hundreds of millitesla of order Tesla. And well, if I only showed you this plot, you could maybe even believe me that I'm looking at Majorana modes. Right? So that's part of the challenge. And this is indeed how the field even evolved. So for instance, on the left here, I show you data from 2012, the kind of optimistic era when this was discussed in the context of Majorana modes. So again, here we have a zero bias peak as this bright streak in the middle inside this superconducting gap. And it comes from the two states crossing and then even splitting again. Here is a couple years later from this Nature Nano paper. Again, similar thing happening, two states meet and then even the zero bias peak persisting for like a Tesla in magnetic field range. And this is definitively 100% not Majorana, it's Andreev states. Why? Because in this later experiment, they actually made on purpose a very small quantum dot. There is nowhere for the two wave functions to separate into two Majorana in that dot. It's a very small dot. If they change gates around, they see that these are all Andreev states, and this can still produce this kind of picture. Right? So this was a conceptual challenge of the field, and a kind of a beautiful in a way, although very frustrating when you work through it, but beautiful that nature gives us two phenomena that can look so similar. Okay, only one of them we are really, really very interested in, although both are actually beautiful pieces of physics. So in the meantime, we identified several different ways how these zero bias peaks can form and stick to zero bias. So Majorana is the first one. There is a topological phase transition, gap closing and reopening inside the big bulk gap of the superconductor. So we always have to live inside this universe while the host superconductor is superconducting. We can only see stuff then. Peaks can even wiggle and oscillate due to finite size of the system and the overlap of the two Majoranas changing. That's called Majorana oscillations. That's still Majorana, that's fine. Quasi-Majorana perhaps. Now this is another situation. Here we have Andreev state, not a Majorana state at all. Coming down at magnetic field, Zeeman splitting, and then hitting zero, and then not splitting after that. Why? Because all these other states above the gap, they just push on the zero bias peak because they hybridize. So the sub-gap state hybridizes with the above gap continuum. They level, repel, and likewise, from the negative side, these states on the negative push up and squeeze the spectrum. So the spectrum gets renormalized and the state can actually stick to zero. Lower left, we have something similar where renormalization happens as function of interactions with other Andreev levels. So we have a red Andreev level, a green Andreev level, and a pink Andreev level. And so we have several of them inside the gap. And when they come close, they hybridize due to some property like spin orbit or just wave function overlap. And the lowest one gets pushed to zero. And the highest ones may not even be visible depending on the fine tuning of your device. And finally, disorder. So imagine we have not one quantum dot with Andreev states, but several. And each one of them has a transition at slightly different magnetic field. Then we get this crowded spectrum originating from different dots. So there's multiple possibilities to get similar data. That's the point. So what to do about all this? Well, I think, so people often have this instinct, oh, well, let's just stop measuring this zero bias peak. It's too confusing. We should do a different measurement. I say we should keep doing the zero bias peaks. Why? Because it's a simple measurement. We already understand it a great deal, and any other experiment you can imagine is harder, and you have to learn from scratch. You'll probably find some alternative explanations for those signals as well. But we can do zero bias peak studies more carefully in a self-consistent way. So I put together this list of 5 properties, 5 criteria. If you satisfy 5, there is a great chance you have found Majorana modes in your experiment. And if you're not working with nanowires, but with a different system, there will be your own set of 5, maybe slightly modified, but with some overlap with my list, right? But I showed you that you look at part of the data, you can fine tune it to look like Majorana, right? So you have to show all 5 in the same device, in the same set of measurements, by the same people at the same university on the same nanowire and so on, right? So the first signature is already talked about, this zero bias peak that kind of comes to 0 and then doesn't leave, right? So that's fine. You want to start with that. Then what else can you look at? Well, in our system, we can explore the spin orbit anisotropy, which is a property where this spin orbit effect is parameterized by an effective magnetic field that points in a certain direction. And that means that external field that we apply has to be perpendicular to spin orbit field to see something, to open this gap due to spin orbit. So if we align the 2 fields, zero bias peak should go away. This can be checked. We have checked it, and we found it on a number of occasions that this is indeed the case. Now, third one is we have these theories from 2010 and then several hundred papers after that have mapped out the parameter space in gate, magnetic field, and other parameters where Majorana should appear. So it is not just tune the knobs and see a peak, oh, it's Majorana. It is actually a space, it's a regime in parameters that can be understood, analyzed, and checked back to a model to see if it makes sense. So the idea is map out where the effect appears and compare it, fold it back onto some basic model. So we have also done that on at least one occasion to find a kind of a region of parameters where zero bias peak appears compared to a simple model. Now, Majorana oscillations, we already mentioned, that's due to finite size. So when we change a gate voltage or magnetic field, the peak should come together, split in 2 peaks, come together again, split. That's when we give Majoranas more overlap or less overlap by changing parameters. A bit like RKKY or Fermi level oscillations, Fermi momentum induced oscillations. The same thing should happen here. Yeah, so you want to see these oscillations and you want to relate them to your control knobs. And finally, the last one is very important and conceptually simple, but a little bit harder to do in experiment. There should be 2 Majoranas in each wire. So you look on one end, you see a zero bias peak. What happens on the other end? There should be 2 zero bias peaks. They should be correlated. Like if one is there, the other one should be there. If one splits, the other one should split. If one disappears, the other one should disappear. And that is this indication that you have actually created a topological region of this Kitaev P-wave spinless state in the entire wire. Now, let's see how we're doing so far. Shuvik, yeah?
Hi, quick question. So, like in addition to that, could you also track the gap closing and opening as a function of the field? Because you should have the, like a normal gap close and then the inverted gap open up, right? And that's where you will see Majorana.
Yeah, so there I make a comment on the bottom of the slides that you could put forward other signatures, also like quantized peaks have been put forward, or the gap closing. So my set of signatures is the cheapest and would already be very convincing. That's my point, right? There could still be some doubt left. As far as in particular what you said about the gap. So for instance, if the wire is a little bit short, there may never be a gap closing. The states from the bulk can just come together and then leave. And also you may not see those states that are kind of bulk because they live in the bulk, right? So if you want to probe the bulk, you have to make a more complicated device. So those are the reasons why I excluded the gap closing from my list. I think without the gap closing, I can already convince myself and everybody else that we have Majorana. I don't know who was next, maybe Arindam.
Yeah, sorry. So I'm surprised that you didn't put the quantized conductance as one of the possible verifications. That is, whether you've got a conductance of 2 square by h or something of that sort. Will that make any?
Yeah, so you know, this has been tried and failed spectacularly, but it also is a kind of a red herring. So this should only be observed in ultra clean wires of infinite length at 0 temperature. Right. So if you put in a realistic model, this just doesn't appear. Right. So theoreticians like this, but it is just not practical to go after it.
Okay. Thanks.
Pratap?
So are you also considering the spatially resolved experiments like STM, which observed the Majorana at the edge of a wire? So what is your comment about that?
Yeah, so in the case of my system that I work with, we can't really go along the wire and probe because the wire is covered in oxide, so we cannot STM along the wire. So I will show you, we make 2 contacts on the 2 sides. In the case of systems like chains of atoms on the surface, yeah, they have an additional control or a measurement knob where they can go along the wire, and they are doing that. So for that system, I would make a slightly different list of 5, and understanding as a function of, you know, position of atom would be definitely on that list for that system.
But for example, the claim by Ali Yazdani, what is your comment on that? Where they had this cobalt atom chain on a lead surface, and with STM they claim to see Majorana at the edge. Do you believe that or not?
So I think it was iron on lead.
Yeah, possibly iron. Yeah,
they have also tried with cobalt. I think with cobalt, actually, they didn't see maybe the peak.
Yeah, possibly iron. That's right.
Which was also interesting and kind of food for thought. So what they saw, you know, 2014 or so, they saw peaks on both sides of the wire. But the wire was prepared in a self-assembled way, so it was coming from a big particle of iron and then sort of spreading out. And also it wasn't one atom thick. And there were also other states along the wire that were not explained. So those original experiments were kind of like our original experiments, you know, promising, but require further exploration. And then they have done a couple of follow-up works. So I think they were on the right track. I have not seen anything recently from Princeton. I have seen nice work from Hamburg and Basel, so Jens Wiebe. They went through the painful effort of picking up atoms and placing them one by one along the chain. And of course, when you do it this way, it's very difficult to make a very long chain, but they've made like 30 atoms or so. And the good news is they can understand completely the spectrum for the chain that they've made. And they even think that there is some evidence that it's there is some topological inversion.
The Hamburg group, I think they did not claim Majorana. In fact, they were claiming that they have not seen the Majorana.
Well, they claim they see topological band inversion, which is already pretty good, maybe better than anyone else can actually claim. But yeah, their chains are too short to really separate Majorana. So, you know, that's the problem with doing a very careful atom by atom assembly, right? It's very hard. Anything can blow the chain off, I guess. But I think that's currently state of the art is from Hamburg. I don't know what Princeton guys are doing. Maybe they're catching up very soon. Or maybe they got sucked into magic angle graphene. Because Majorana is not magic, and graphene is magic.
Okay, thank you.
All right. Okay, so let me show you an overview. So I gave you 5 signatures according to me. So you can argue with me about the signatures, but already my signatures are a pretty easy list. You have to do always the same measurement, just do it on the same wire in the same group, right? Not 1 year and in one part of the world and then next year in another part of the world demonstrate another thing. That can be fine tuning. So here we are. The green cells are positive claims of observation of my signatures. And you can see nobody has seen 5. People have seen 2 or 3 on many occasions. And in particular, nobody has seen the signature number 5. The correlated zero bias peaks on the 2 ends of a nanowire. So that's where we are, right? So we have a method. The method is very powerful. If you apply it this way, you can see that the proof of Majorana is still lacking, but the method tells you that you have not proven Majorana yet, right? So the method is good. And this is the epitome of our method, is using devices like in this picture. So almost the same as before, just really here's a nanowire and a superconductor and a tunnel contact on the left, and there's just another one on the right. So there's 2 of them, left one and the right one. And what you can do is, well, you can, for example, apply bias to the middle and send current to the left and right, and look at the simultaneous correlations of your signal on the left and on the right. So if you have 2 Majoranas, like gamma 1 and gamma 2 here in the picture, then you should see some correlated evidence of that. And well, when we do that with our best fabrication practices on these devices, we just don't see the correlation. We can see a zero bias peak on one side. For instance, here on the left, we see a zero bias peak appearing at 1 Tesla. On the left, it is even of the quantized value in this particular example, or quantized value of 1 for the person who asked about that. Now, on the right side, at the same time, measured simultaneously, we see a dip. There is no peak. There is a dip. And in general, there is peaks on both sides, but they are not correlated. So this plot summarizes that the onset of the peak on the left and on the right, the red and the blue dots, are different. There is accidental coincidence sometimes, but there is no statistical or consistent meaning behind this. It's just accident. So I could, in principle, tune to this gate, show you zero bias peaks on 2 sides, and publish a Nature paper saying that I found 2 Majoranas. But I have not done that. I published a Nature physics paper that says I have not found the 2 Majoranas. So all this and some verification studies that we've done on other people's papers led me to a lot of thinking, philosophing about what we're doing, why we're doing it, and how we're doing it. And I wrote a couple of opinion pieces, and one of them is in physics. So it is kind of a cautionary piece. Be careful if you think you've discovered a new state of matter. Just double check and run some consistencies. And it summarizes my thinking in this very qualitative rough diagram where I put some topological phases, the famous ones, versus energy of the phase. So the higher the energy, the higher the temperature, let's say, that we can see them, and disorder. So disorder, good disorder is on the left and the bad disorder is on the right. So that makes a triangle in the upper part where we want to be. We want to be here with high energy and low disorder. And that's where we find some of the things like quantum Hall effects, topological insulators can be seen at room temperature. And there is no doubt that those phases have been demonstrated. And then something very delicate like interaction-driven phase like parafermions or something like that, SYK model is just such a small energy scale. And also complicated devices, which means a lot of disorder. That is just no chance that you can see it at the moment with present technology. No chance. And Majorana is kind of on the boundary, and fractional quantum Hall effect is dipping here because of all this. Anion experiments are still inconclusive. It's on the boundary. So its energy scale is about the superconducting gap, which is a fraction of a millivolt, and disorder is hundreds of nanometer scale, mean free path or so in the best devices. And it's a long cloud in terms of disorder. And so the region, I call it the fog of hope. The fog is from the fact that the signatures are foggy. You think you see something, but you cannot be sure. But of course, you hope that you discovered something important, and it pushes you to convince yourself and try to convince others that it is it, right? And so this is a delicate, tricky game to dig things out of the fog of hope. You can get lost in the fog of hope. Really, you want a way out of the fog of hope. So the way out, the diagram shows it. You have to go this way. And how do you go this way? Well, you adjust the materials properties of your system, because we already have a method. Remember, we have this 5 criterion method from zero bias peaks, how to tell Majorana when we see it. So now on the materials side, if we make the materials better, we can increase the energy scale. We can also reduce disorder and move ourselves out of the fog of hope. So we have a list of ideas for what to do in terms of materials properties, and it's a long list. It might not work, in which case at some point we'll give up. But for now, we have good ideas and good people working with us on the materials. So for the last few years, I have been essentially a materials scientist, materials physicist, understanding TEM images and X-ray diffraction and elemental techniques like EDS, atom probes and things like that to figure out what gets us into a good Majorana regime. So, and also first principles calculations and things like that. So we have something to be proud of. We have made some progress. At least we shook the tree a little bit from the paradigm. And I already showed you the tin wires, but here's some data where we've used the same indium antimonide wires, but we put a new superconductor on it. Well, tin is not new by any measure, but in this context, it's a new layer that we put on semiconductor, and it was a collaboration with UCSB and Eindhoven and Grenoble. So it was a large effort. And yeah, the data look good. This is the induced gap in this material. So you see the same peaks as I showed you before. They're at higher voltages, and inside the peaks, conductance is very low. So we call it a hard gap. Now this hard gap survives to pretty large magnetic fields, at least a couple of Tesla. There is no current at zero bias. So these are all good news for having a good starting point for Majorana experiments, maybe even for qubits. But one of the most surprising things we actually learned from this is that, well, tin and indium antimonide, the lattices have no relationship in our case. So actually, tin and indium antimonide are lattice matched when it's alpha tin, but alpha tin is not superconducting. So beta superconducting tin is not meshed. And the shell is granular and all kinds of imperfect, but still gives good data. So maybe this epitaxial relationship, the match between crystal lattices, is not crucial to see things like this hard gap. So I have not introduced these things to you, but if you heard about the materials challenges of this field, then you may have heard that you need epitaxial interfaces, such as aluminum and indium arsenide, for example. And we show that maybe that's not necessary. But other things are necessary, like careful cleaning and so on. Now, what about braiding? Well, this remains a long-term goal. It will be a very big effort. Collaboration of many different specialists from materials and engineering and physics and theory and experiment. I would like to be part of that. And we are kind of slowly working towards that step by step. While we don't have braiding devices, we're not even sure we've demonstrated Majorana yet. We do have quantum computers, not the Majorana ones, but superconducting quantum computers. And in particular, IBM is a company that probably a lot of you know has made their quantum computers available to people, which is wonderful. So we used an IBM quantum computer during the pandemic when the lab was shut down to model a Majorana braiding operation on an existing quantum computer. This work, in the end, I fell off the author list because they got too excited and did all the work without me. But it's a work of our postdoc, John Stenger, with David Pecker, who is a theorist, and a couple of IBM guys, Nick and Daniel. And when you have friends at IBM, they not only let you have access to the quantum computer, they let you hack the quantum computer. And in this case, it meant creating new gates that they did not have in the kit. So going in and reprogramming the pulses for the gates, they let John do that. So that was awesome. Now, the basic idea here is something called Jordan-Wigner transformation, which transforms you from a Kitaev chain to a chain of spins. And spins are like superconducting qubits. They're kind of bosonic states. So the Jordan-Wigner transformation takes you from this picture to this picture. So gamma operators map onto sigma operators, which are the qubit operators. Now, why we needed to change the gate set? That's because the middle side for this braiding operation is a coupling of 3 sides. And to do the quantum dynamics of that process, 3-way process, you need a lot of CNOT gates. And the CNOT gates are very costly. Each CNOT gate comes with a 1% error in a current quantum computer at IBM. So you can only have like 25 of them before you get a random outcome of your computation. So instead of, and a CNOT gate is a conditional flip of the 2 qubits. So that's a big angle operation. That's why it has a big error. So they replaced it with a small angle 2-qubit operation A theta. So these A thetas here are new gates that John created with help of Nick. And that allowed us to do allowed them to do the full braiding operation in a quantum computer. Now these gates are part of the new set of Qiskit Nature. Qiskit Nature is a set of protocols for running physical simulation like the Jordan-Wigner transformation more efficiently, right? So with small angle rotations rather than big angle rotations. Okay, so like I said, this was fun. We did some braiding with imaginary Majoranas, simulated Majoranas. And of course, what we learned, most of it, well, the data is just kind of anticlimactic. We wanted this state psi plus to be the largest, and it was. What we learned is mostly how to use the quantum computer than anything about the actual braiding and whatnot. But it was a good experience to at least follow from the sidelines how they did it. So that's the end of my talk. We have not discovered Majorana. We should be able to do it with some materials improvements, if that works. There is challenges ahead. The good news is that we have a good method to identify if it is Majorana or not in any given nanowire. And yeah, I will keep you posted and happy to answer any questions. Thanks so much for tuning in.
Great. Thank you, Sergey, for the excellent talk. Are there any questions from the audience? I know we already asked a few, but if there are any questions, please unmute yourself and go ahead.
Shavik, Sergey, I had a question. Rajdeep here. So I was wondering that you talked about these two Majorana modes at the two ends, and this measurement. Is there a way of taking signals and interfering out of these two things? Is that something that is feasible or not? Cannot be really thought
Yeah,
of?
there are some theory proposals. So you can make all kinds of fun experiments. Once you establish Majoranas, that those two signals are Majoranas, you can do things like electron teleportation. So electron enters on one end and exits on the other, kind of because it's a shared mode. You can do interference if you put the wire in a loop. You can deduce from interference patterns that you have something non-trivial going on. So the periodicity of patterns will change if there's Majorana. You can also do real-time correlations, like send an electron and see how it splits between the two sides and learn that this is Majorana. This is all in the future. Seeing now from the basic DC static spectroscopy measurements of zero bias peaks, we have to identify that this is plausibly Majorana. Then we explore the quantum interference properties, the dynamics of the states, the braiding, the fusion, and so on. Teleportation.
Thank you.
Vijay?
Yeah, hi Sergey, thanks for the nice talk. Somewhere along the way, you had mentioned, the choice of using the zero bias as your signature versus some other possible techniques, and you said that zero bias is still good. It's easy to do, but you have to look for all of these things. Are there other leading proposals which people have tried where it's less possible to get confused with signatures which look like Majorana? Are there such experiments? Especially with a lot of development in the superconducting qubit community, there are lots of sophisticated measurements one could do using microwaves and things like that. Are there any such leading or promising ideas out there?
Right. So as far as deploying the actual know-how from the superconducting qubit world, no, not much. And I agree that could be powerful and interesting, for instance, because the energy resolution of the technique is much better, right? So we can resolve nanovolts with microwave domain measurements. So we can look very finely at the spectrum inside the nanowire. So people have done such experiments on nanowire Josephson junctions, beautiful work from, let's say, Saclay or Yale or Delft, but have not found Majorana this way, let's say. So they're trying. As far as other things that people talked about, the answer is no, again, according to me. So you would appreciate it, for instance, in Josephson junctions, looking for Shapiro steps that go missing. So you have a ladder of Shapiro steps at Josephson frequency fractions like 1, 2, 3, 4, 5. And then let's say the first one should be missing, the third one should be missing, the fifth one should be missing if it's a Majorana Josephson junction. So this has been found, but in my lab, we have found similar missing steps without Majorana. Say in nanowires at zero magnetic field, so without one of the ingredients, the steps are still missing. Right? so the point is, you go to a different method, and if your spectrum still has other states that are not Majorana, they will manifest, and they have a potential to obscure your signals, right? So you really have to clean up your device so that the Hamiltonian you have in your head corresponds to the Hamiltonian of your nanowire a little bit better, and then you can start to distinguish what you got there.
Okay, all right, thank you.
Any other questions? Maybe I can ask. So in this all the zero bias peaks, all the literature that is out there. So the mostly you find like they're talking about at one end of the wire, not necessarily looking for both the like Majoranas on both ends. I mean, is it something that people were not really looking for, or are there some like technical challenges to actually do this kind of measurement simultaneously?
Well, it is a little bit harder, right? You need all the contacts to work and more gates. It is harder, but it's not fundamentally harder, right? So it took a while to realize that's what you need to do. Although, I mean, we already wrote down the list of measurements. I wrote it down when I was still a postdoc in Delft, like 2012 or 11. And that was one of the top things on the list, to do a 3-terminal measurement. But still, when you starting, I mean, it's mostly social issues.
Okay. Okay.
And then, frankly, sometimes, we or others would make a 3-terminal device, but it would only make sense on one side.
Okay. Okay.
Yeah.
Got it.
So then maybe just publish the one side, not show the other side. Things like that. Yeah.
Surajit, you have a question?
Hello, sir. It is a nice talk. I have a very small question. So you have shown a cartoon picture where you have shown the two mode, a red and the green, and the end of the side. I want to know that this decay of the characteristics length, anyone can estimate for a given a particular choice of material, that how long one should need that it will decay before they are overlap?
Yeah, this is not a small question. So, of course, I can write a very simple model with the 1D, one band, no disorder, and put in some parameters like spin orbit and superconducting gap, and get some idea, right? But then there are so many unknowns in actual devices, because we cover the wire with a metal. It's very difficult to know what's going on under that metal, how the metal dopes the wire, how many subbands are there, how the wave functions hybridize, what kind of disorder is there, which way electric field is pointing to create spin orbit, just to name a few. So it's been a bit of a hunt in the dark for a while, and now we are getting slightly better hold of it with more comprehensive modeling, which is a kind of extensive 3-dimensional tight binding, or Poisson-Schrödinger, or even first principles being deployed, RPES, people trying all kinds of things to nail down all these parameters. And then there is the kind of just a purely experimental track. For instance, I make devices of different lengths, and do I see the same thing on the two sides or not? Right? So I can tell you that if it's, let's say, 200 nanometers for a 100 nanometer wire, right? So 2:1 ratio. I see the same thing on the two sides, more or less, not even perfectly. If it's 400 nanometers, I see different things on the two sides, but sometimes I also see the same things. And then if it's 600, I haven't even tried, because I already convinced myself that at 400 we are seeing different things. Right? So that's the experimental answer.
Thank you so much.
Thank you.
Any other questions? Okay, maybe another quick one for me. I don't know if Sergey wants to share, but so do you have any proposal or in mind, like how one should go ahead to do with the braiding? Is it too far ahead at this point?
I mean, I can give a strategical answer rather than like this is how we do it, right? Because I mean, first of all, I think you need to prove Majorana, then do braiding, because this is like $100 million effort. And if you didn't have Majoranas at the start, then you're just going to waste this money. And what you're going to prove is that you don't have Majorana.
Yeah.
And some people say, well, only braiding can tell. No, it's not the case, right? I gave you 5 signatures. These 5 signatures with simple measurement can tell you. Just do the 5 signatures before you do braiding, okay? So that's the first point. Second point, let's still be optimistic that we can do braiding in the future, right? Then we need to prepare. What does it mean? It means for braiding, we have several modules. We have just the Majorana and the material science of it and the physics of how to generate them with high yield in the nanowire. Then we have the manipulation module. So take the two and move them around, right? That's non-trivial, right? We don't have a off-the-shelf module for doing this kind of thing. It's not something we can borrow from CMOS or anything like that, or from the cell phone industry. We have to create this. So we can start on that already now. We can study multi-terminal Josephson junctions or nanowire networks and ways to control some kind of states in them. Maybe not Majorana, maybe Andreev, but some kind of states.
Manipulation.
Manipulation, and then the readout, right? Quantum readout. So this now I was showing you just electrical measurements of current. We could do one step ahead with microwave. That can still be classical, just kind of like gigahertz impedance measurements. Then there is the true quantum, when we do single shot and we understand the outcome of the braiding. Has the ground state been changed or not, right? That requires most likely an integration of an ancilla qubit with a Majorana qubit. So for instance, a transmon or a fluxonium or a spin qubit or a charge qubit, some kind of very sensitive quantum device that you can then couple, and it can read out the state of the Majorana qubit. So that means with a semiconductor and a superconductor technology that we are pioneering, it does not exist before. We need to integrate all the state of the art from the qubit world into the same device. So we can start on that now as well, right? For instance, we can make a transmon based on nanowire. People have done it, and see if it can survive magnetic field that we need, or something like that, right? So we can start on all these things, and there will be some interesting things to study and discover. And it all leads to braiding. Once we have all the components lined up, we can get together in a big lab, ask somebody for $100 million and do the braiding.
Yeah. Okay. Shurajit, you have another question?
Yes, I have another question. So there is a very few experimental knob one can have, like you use the magnetic field or electric field. I was curious that is temperature is another knob. Is the changing the temperature, does it resolve any kind of a fundamental issue that one has in that scenario?
So first of all, electric and magnetic field is like 1/2 of all fields, right? The other one is gravity. Or I guess there's a strong interaction too. So that's not so little. We have multiple gates, right? So there's multiple electric fields. There's also field angle. So that's quite a few control knobs encoded in this, right? Also source drain bias. But I mean, temperature, what's going to happen is things are going to broaden and die. And so I think at this stage, it is not one of the more useful ones, because temperature just typically confirms what you can see at the lowest temperature. Let's say if your peak width is 20 microvolts, and at 100 millikelvin, it will disappear. Things like that. But in the future, it can be a useful control knob. For instance, if we establish this topological gap we talked about, we can study to what temperature topological protection extends, and that could be also a measurement of this gap. We can also study, some people propose some thermoelectric signatures. So that could be temperature dependent.
Okay. So just this last question, I didn't understand this point. That's why I'm asking you. So this semiconductor, or the deposition, the superconductor on a semiconductor nanowire, the interface is considered as a metal superconductor interface or metal semiconductor interface, because semiconductor also have an intrinsic band gap. So sorry, I didn't understand it. So that
there is also several different gaps that I'm used to, but I did a poor job introducing. But basically, it's a metal semiconductor interface. The metal only goes superconducting at the lowest temperature, like 1 Kelvin or 5 Kelvin, something like this. And the semiconductor is doped typically into the conduction band. So you just sit above the gap by a few tens of millivolt, or just a few millivolt in the best case, above the semiconductor gap. And then you open a much smaller gap. So semiconductor gap would be, in this case, 200 millielectron volts, 0.2 volt. And then you open a 200 micro electron volt gap, which is 1,000 times smaller, around the Fermi energy that sits in the conduction band.
Okay. Thank you so much.
Thank you.
I think we have asked a lot of questions. Are there any last question that people might want to ask? Okay, if not, thanks Sergey again for this wonderful talk, and also taking your time out for this lecture.
Thank you so much. Thanks for the questions. Thanks for attending. Thanks for the invitation. It was fun to talk.
Yeah, hope that this pandemic ends and we might have you over here at some point.
Yeah, we'll see you. We'll see you at some point somewhere. Bye-bye.
Thank you. Thanks, sir. Bye.